Hey, Honest Statistics. This is Mr. Kim. Sorry, this video is long overdue, I know, but I'm going to just go through with all the review questions that I had for you guys before passed up for you guys in the packet. I hope this video helps in terms of preparing for the exam that's going to be coming up on Monday. So let's get right on to it. Make sure you guys have the calculator on the side. So I'm going to show you guys on side by side as to what I'm expecting for you guys to do for the day of the test. So for this question here, the very number one, I would say, here I'm just going to do markup. Okay, so the average number of calories in the Yum Yum Good candy bars is 210 with a standard deviation of 10. So right away, you know that this is 210 with the standard deviation of 10. You can go 10 in either direction. Now, I'm not really expecting for you guys to all fill in these blanks here, but just to have a general idea of what the graph is going to look like, the normal distribution, I mean. If the number of calorie bars normally distributed, what percent of the bars contains more than 225? Now, if you take a look here, 225, it should be somewhere around here, but we're talking about having more than 225. So we're actually shading in this area right there. So if we're ever asked to find out the percentage of something, you know that you're supposed to be using normal CDF. So on your calculator here, I'm not sure why. Okay, so I'm just going to refresh the screen. All right, so this is not really working so well, but I'm going to show you on the calculator. So second var, so if you guys are wondering where I got to that, so you press second, the blue button top left, and then press vars like this. So you're going to go to normal CDF. Now, the lower and the upper boundary here is 225. The reason for that is because if you take a look, the lowest boundary for that blue area is going to be 225. And you want to pick a number that's really far away from the 3 standard deviations from the normal distribution curve. If you actually calculate where the first, second, third standard deviations are, it's 220, 230, and 240. From the mean, you move 10, 10, and 10. So we want to put a number for upper that is actually way further than 240. So like 300 or even 3000 or anything like that beyond that should be good. As long as it's more than 240, you should be fine. The mean and the standard deviation, you're just going to simply copy and paste that. So the answer here, as it turns out, is 0.0668. Now, when you guys get this answer on Monday, you have to be able to tell me that that's about 6.7%, which closest to being D for this one. Okay. All right, next question. The observed times in the text runner are normally distributed. Z-score of his running is -2. You have to understand that the Z-score is the number of standard deviations. It's the number of standard deviations you're away from the mean. That's how you always want to remember the Z-score. So if they say it's -2, you're not moving 2 minutes lower or percentages or anything like that. You're literally talking about 2 standard deviations, like how answer choice D and E says it, but it's got to be lower than its average time. It's from the center you're moving 2 standard deviations away, the center always being the mean. So it should be D for this one. Okay. Number 15. A lot of you guys asked me about question number 15. Mean of 3 to 50 customers with the standard deviation of 320. Find the range of the middle 50% days. Now, the middle 50% is a fancy way of saying an IQR, because an IQR measures from the 25th and the 75th percentile. If you actually calculate the amount that's in there, if like 75 minus 25, that accounts for the middle 50% of the entire data points. So when you actually go to figure this out, you have to use inverse norm for this, because you're given the percentiles. IQR, always remember it as the 25th and the 75th percentile, and then you're going to figure out what those numbers are. Of course, the mean and the standard deviation is always provided for us, so you're going to be using that and capitalize on it. So go to second vars on your calculator. You're going to go to inverse norm, which is number 3. The area that they give you is 0.25. Now, I know your calculator might be different from the test. You don't have a tail. Just leave that alone. It always should be on the left. The mean of 3,250 and the standard deviation of 320. If you're wondering about why did I put 0.25, it's because for the first IQR, the Q1 is always at the 25th percentile. So you put 0.25 always for the area, please note that it's got to be in a decimal format. So you put the 0.25 in there, and then press paste. And then you're going to get 3,034. So 3,034 should be your lower boundary for Q1. And then what I'm going to do is I'm just going to copy and paste that and just scroll to the left and just change this to a 75%. And then you get the 75th percentile at 3,465. So with these two numbers in mind, remember that's your Q1 to Q3, middle 50% range. So the only answer that matches with what we have here is going to be answer choice A. Okay. All right, moving to the next question. For this, it should be very simple, where we have a mean of 12 and a standard deviation of 2. Remember, a normal distribution curve always want to go left and right by 3 standard deviations from the mean. If you actually were to mark every halfway through between those, a little normal distribution curves, if the mean is 12, it can't be here, here, nor there, because that's not 12. That's somewhere between 15 and 20, somewhere between 20 and 25, 0 and 5. So you can eliminate all of these choices right out of the gate. Now, the second question is, if I have a standard deviation of 2, from the mean, I should be moving 1, 2, 3 standard deviations away, and that should reach up to, whatever the highest value possible that this normal distribution ends. So if it ends at 12 and the standard deviation is 2, 14, 16, and 18, we're looking at where 18 should be the cutoff line on the higher end. It seems to me distribution 1 really fits that description well. But for this distribution 2, if I move, like, let's say this is 12, then I move 14, 16, and 18. Notice how 1, 2, 3 standard deviations is around lasting around more than beyond 20. So distribution 2 is just way too large of a spread for it to have a standard deviation of 2. Therefore, the correct answer here will be distribution 1. Very similar to the question we did, or one of your classmates explained for the scavenger hunt question. All right, next. The appraised houses, the mean of this, standard deviation of that, the teacher's contract, blah, 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 they need to actually need an extra 10% of the funds compared to the previous year. So that's the context. They say to raise this additional money, they raise all appraised houses values by 5,000. What that means is that all the values of the houses, or the appraised values, they get added by $5,000. When we talk about adding or subtracting to all the data sets, remember that the only thing that changes is the center. So while the mean will get increased by 5,000, the standard deviation does not change because we're only adding and subtracting. We're not multiplying by anything. So what will be the new standard deviation? Doesn't change. So it's still going to be the same old $23,000 for the standard deviations. Moving on to question number 32, the distribution of the weights of 16-ounce bags. So we're going to say that, generally speaking, we're talking about a mean value of these potato chip bags to be about 16 ounce. And then the standard deviation of 0.28. They say, how does the weight of a bag at the 40th percentile compare with the mean weight? So if it's a 40th percentile, again, I'm given the percentile, which means I gotta use the inverse norm for this one. So if I use inverse norm of, let's say, the area of 0.4, because that's 40% in decimal form. So I go to inverse norm here, put 0.4 with the mean of 16 and the standard deviation of 0.28, and then press paste, and I get about 15.929 ounce. That is the weight of the bag at the 40th percentile. But it says, how does it compare with the mean weight? Which means I need to subtract from the mean, which is at 16. I'm going to compare, which means I'm just going to subtract. So it gives me about 0.07 of difference. So it's 0.07. Oh, it's 0.07 actually below the mean, because that value is 15.9 and the mean is 16. So mean is higher. So it's got to be below the mean. Okay. The fourth page, I just completely disregarded that. And so now we're moving on to this. This is cumulative relative frequency graph. So cumulative relative frequency graph. This is what we did back in chapter 2.1. Very long time ago, I know. But all you have to do is just understand that the top is always 100%. The bottom is 0%. And you figure out where in this particular case, the 90% of the day. So you just go to the graph and it's kind of like a map. I'm just going to kind of scroll through the 90th percentile, which is somewhere between 100 to 80. That seems to me somewhere around 20. So you're just going to say, how many rooms must the hospital have available? About 20. So it's just kind of like matching. Okay. So we are going to go to the next question, which is this. A store offers shoppers who can, I don't need a calculator for this, so I'm just going to zoom in. We have the value 10 times the card number plus 5. When we're doing this question, it seems to me that there is a multiply by 10 and the plus 5, and we're applying these changes to all of these values on the table. When we're multiplying, everything changes. We already established this back in 2.2. This one only center changes. So when we're talking about the mean of 2.6 and a standard deviation of 12.1, what must happen is that these two changes must apply to the mean, whereas only this gets applied to the standard deviation. So 10 times 12.1 actually gives you 121 for the new standard deviation. What about the plus 5? We don't care about that because only center gets impacted by that. So that you're going to multiply that by 10 and then add the 5. So this actually becomes 26 plus 5, which is 31. So the new mean of 31 and a standard deviation of 121. So I'm going to eliminate A and B because the mean is not 31, but the only one that makes sense is E from that point onwards. Okay. All right, now we're on to these open-ended questions, if you will. So the open-ended questions for this, we already went over, but let me just do this again. Draw a normal distribution curve. Again, we have to be very comfortable drawing these. We have the mean of 100. Sorry, the description is down here. Standard deviation of 15. So 115, 130, 145. Then we have 85. Then we have 70. Then we have 55. Okay, so we keep on adding by 15s and then subtract by 15s. So what score would you have to get to qualify for the Mensa International? That description is way up at the top. In order to get accepted into the Mensa program, you got to be a top 2% in terms of the IQ score. So in order to be a top 2%, which means it gives me the percent, anytime it gives me the percent, I'm going to use inverse norm for that. So go to your calculator, use inverse norm with the area of being 2%. Please type in 0.02. The 2% is not 0.2. 0.2 is 20%. Therefore, 0.02 should be 2%. So I'm going to bring out my calculator on the side, use inverse norm, 0.02 with the mean of 100 and a standard deviation of 15. And then it gives me that the IQ score for that is 69. I think I made a small mistake here because if I do 2% at the very least, from the left-hand side, that actually gives me the lowest 2% where I want actually the highest 2% here. So if I want the highest 2% in here, the top 2%, I can actually change this to the right-hand side of the curve, which you guys are not going to have access to that. But the opposite of 2%, but if the 2% is at the top right, I mean, at the top side, then the rest of this starting from the left, this should be about 98% of the entire data. So we're going to type in 0.98% because the top 2% can be interpreted the same way as being at the 98th percentile. So when you actually type that in, so it's going to be 100. So this is 98, comma, the mean of 100 and a standard deviation of 15. So this would be 130.8, which turns out to be an IQ score of 131. That's what you need to have in order to qualify for Mensa. Okay. Of course, please don't leave it like this on the day of the test. I know that I'm like really excluding a lot of the things, but give me a sentence or two describing like what this is. So you need to have an IQ score of 131 to get accepted to Mensa or something like that. That should be sufficient enough. Okay. These are all open-ended. So not just the number, but the sentence. I need that. I need that from you guys as well. There are about 328 million people in the United States. How many Mensa International geniuses live in the United States? This is a very simple question because you just have to take 0.02 times 328 million people. The 0.02 comes from the fact that I'm taking 2%. Remember, the top 2%, you can think of it as only 2% of the entire population can be accepted. So it's taking like 2% of the 328 million. So if I just type that into my calculator real quick, 328,000,000 times 0.02, I get about 6,560,660,000, which is about 6.6 million people gets accepted to Mensa. Again, give me a sentence or two describing what you have just found out in terms of the context. Next question was the basketball question, right? So when we're actually comparing three athletes from three different eras, three different times, we always want to compare what we call their z-scores. It's very relevant to the question that you're going to do on the next, as an actual AP free response question. So here we want to find out the z-score for Wilt, Jordan, and LeBron. So remember, the z-score formula is always the value minus the mean over the standard deviation. Applying all of those things, that's the value of Wilt, that's the mean, and that's the standard deviation. So all you got to do is just type that in as such. 30.1 minus 10.8 divided by 7. But I made a small mistake here because if you do that, it's not going to give you the correct answer. So you have to tell the calculator to, hey, subtract those two values first and divide by 7. So it actually gives you 2.757 like this. For Jordan, it will be 30.1 minus 8.7 divided by 5.9. So I can put in parentheses first if I want to type it all in one get-go. So if you do that, then the calculator understands it as, okay, so you want me to do 30.1 minus 8.7 first and then divide by 5.9, which gives me a z-score of 3.627. And then you'd find LeBron's as 27.1 minus 8.4 divided by 5.5. Okay, so the z-score for LeBron is about 3.4. I'm just going to write this down for you guys so you guys can see what you have to type. So by comparing the z-scores, we can obviously see that who was the GOAT? Explain your answer based on the z-score. You always have to make sure that you base your answer on the z-score. So Jordan, because his z-score was the largest, he deviated away from the norm, the average from everyone in the league during that era, which made him the best. In certain regards, I'm skipping over that sentence, but that's what I need you to say. Because the z-score was the greatest. Because he deviated away from the norm by that much further away. This one I'm going to skip because, Adam Morrison had this. You can find out the z-score and figure out that actually gives you sometimes negative z-score. When you have a negative z-score, it means that this certain player did actually worse than the rest of the guys in the league. So that's what it means when it says interpret the value of the z-score. If it's a negative value, you go actually below the mean. So you did actually worse than everyone in the league. All right, last question here. So we have, I'm going to zoom into this actually. Speed is measured by the time required to run a distance of 40 yards. So time to run a 40 yards, we have mean, standard deviation, we have also a minimum value. Based on the relationship between the mean, standard deviation, and the minimum time, is it reasonable to believe that the distribution of 40-yard running times is approximately normal? And we want to explain that. So when it's normal, what that means is that it follows the empirical rule. A normal distribution curve should always follow the empirical rule of 68, 95, and 99.7%. If you were to actually draw this out using what you know from the empirical rule, so the mean is 4.6, and then you're moving by 3 standard deviations to the left and the right. So if you move 3 standard deviations to the right, let's say 4.75, 4.9, and then that would be 5.05. Just to make sure, yeah, that should be good. Then it's 4.45, 4.30, and then 4.15 when you actually subtract it. All right, so based on the relationship between the mean, standard deviation, and minimum time, is it reasonable to believe that the distribution of 40-yard times is approximately normal? The answer to this, I believe I said it was no. And here's the reason why. If they said the minimum is 44.40, that makes no sense because the minimum value that actually contains about, most of the data, about 99.7%, almost 100% of the data, should go as low as about 4.15 in terms of the seconds based on the mean and the standard deviations. But that's not what they have. They said the mean is 4.4. It's a bit too high. That's only about moving 1 standard deviation to the left, which is not going to be sufficient, unfortunately. So we're going to say no, because following the empirical rule, the 3 standard deviation to the left, the value or the time is 4.15 rather than 4.4. I mean, this is just one way to say it. I know that the answer key says something different, but the main essence is the following the map and looking at how the minimum doesn't coincide with the lowest possible value in the empirical rule. All right, so calculate and interpret the z-score for a player in this position who can lift 370. So remember, z-score is the value minus the mean over the standard deviation, 370 minus 310 over 25, so 60 over 25. All right, so this is where my calculator comes into play. 60 divided by 25. I'm gonna just convert that to decimal, so that gives you 2.4. So this means that this certain athlete or a player has weight lifted 2.4 standard deviations away from the mean. Remember, that's what this z-score represents. It's the amount of standard deviations that you are away from the mean. So if you were to actually draw this out, mean 1, 2, 3, 1, 2, 3, this particular player holds somewhere around here, because that's 1, 2.5 of standard deviations moving away. So you can say that this active player is pretty good, moving 2 standard deviations away from the norm, which is right in the center. Okay, now this last question, you're actually trying to compare player A to player B, and this is actually a really tough question to do. So if I want to find out, based on the information, the means and standard deviation, all of that, which one would you actually should choose? So unfortunately, even though this doesn't really follow the normal distributions, we're still going to use the mean and the standard deviation they provided for us. So for the time to run 40 yards, the mean of that, I believe, was 4.4 with the standard deviation of 0.15, if I'm not mistaken. No, I'm sorry, 4.6. So I'm going to fix that. And then the amount of weight lifted, the mean of that was 310 with the standard deviation of, what was it, 25. All right, so let's talk about player A. So when we're comparing two athletes, just like how we did for the previous basketball questions, we always want to use the z-score. So z-score for, let's say, running, it's 4.42 minus 4.6 all over the standard deviation of 0.15. So remember, because for time, it's actually a little bit different, because the shorter your time, the better you are in terms of running, because that shows that you're faster. So this actually comes out to being, let me use a calculator here. Zooming into this, 4.42 minus 4.6 divided by, oops, I have to first do that, divided by 0.15. That should give me negative 1.2. Again, please don't do this. That's not the correct answer, because you forgot to put parentheses around that if you're going to do that. So put a parentheses around the first two subtraction, then divide by 0.15. You should get a z-score of negative 1.2. And then the z-score for the weights, let's do the same thing. We have 370 minus 310 over 25. Oh, that's actually the z-score of the previous one that we actually found out, which was 2.4. Now, for player B, we're going to do the same thing. Z for running, Z for weights. So player B has 4.57 minus 4.6 over the standard deviation of 0.15. So 4.57 minus 4.6 divided by 0.15. So we have a z-score of negative 0.2. Now for the weights, we have 375 minus 310 over 25. So that should be 375 minus 310 divided by 25. So we get a z-score of 2.6. All right, so we got all the calculation stuff out of the way. Now let's really just compare what's happening. Remember, if you're comparing the straight up z-scores between the time, this particular player is about negative 1.0 standard deviations farther away from the player B's point. How did I get negative 1.0? Just subtract these two numbers, negative 1.2, negative 0.2. This particular player is better than player B by 1 full standard deviations away from the mean. What that means is, if this was, let's say, where player B was, this is where player A is in terms of moving 1 full standard deviations to the left, which gives you a really much faster time in regards to the running time. Now, if you compare the z-scores of the weights, that's about only 0.2 z-score of difference. So even though player B can weight lift a little bit better, though the magnitude of that little bit is way smaller compared to how much faster player A can outrun this player B. So therefore, player A is definitely the better player because even though the weights for the player B is better, the z-score difference is not quite significant compared to the z-score difference between the running of the two players. If you read the descriptions of what I wrote down for you in terms of answers, that's all it's talking about. It's talking about how you're comparing the z-scores and how z-score for player A is just so much better in terms of running by full 1 standard deviation, by full 1 z-score. Therefore, this is a no competition. You want to use player A. If you're the owner of the ball club or the owner of any athletic teams, you want to pick player A based on the statistics that you see. Okay, so again, this was an AP caliber level question. For your test, it's not going to be up to this, but it will be a good practice for you guys to do. In the meantime, I hope this video helps in preparation. Like I said, study over this weekend, and I'll see you guys on Monday for the test. Thank you so much, guys.